This video is about fitting models of impedance to data from loudspeakers. The video accompanies section 29.2.2 of the book, but it uses a different example than the one in the book, so it's useful to just watch the video and read the book both. The combination of the two examples is stronger than either one by itself because they use slightly different fitting methods in the two. The loudspeaker that we're using for this example is this oval 8-ohm loudspeaker that we looked at the data for once before. This is the data that we had there, and what we're wanting to model is the primary resistance and impedance-like behavior here, inductor-like behavior here. It's not quite an inductor, so we're going to use the nonlinear impedance formula that we had. We'll also want to model the resonant peak down here, which is the primary resonant peak. We will not bother modeling this small secondary resonance here. And we will try to model a little bit this extra sort of electrical resonance that we have here at high frequency, but not so important this sort of weird behavior that we have at even higher frequency. So we're going to be wanting to model from about 50 hertz up to about 5 megahertz. At the end, maybe I'll look at how to model this extra little dip at the end here. The data that I have is actually in two files. One file swept the entire range here from 50 hertz to 10 megahertz. Another one, because I wanted to model this mechanical resonance here very precisely, I did much smaller steps over that range from about 100 hertz to I think it was 250 hertz. So we have a very detailed view here, and we'll want to use that detailed file to fit the mechanical parameters that do the mechanical resonance, whereas we'll use the entire file to fit the rest of them. In addition to looking at the magnitude, of course, the impedance spectroscopy also gives us the phase. And we have got the mechanical resonance here doing sort of an increase in phase and then decrease in phase, going through 0 right at the resonance. We've got a gradually increasing phase through here. Again, there's this secondary resonance that we're not going to bother try to model. The peak of the phase here is only about 53 degrees. Now, if we were looking at a resistor plus inductor model, we'd get all the way up to a 90 degree or very close to a 90 degree phase here. So this is why I'm saying that we're going to use something other than a simple inductor, the nonlinear model that we've got, to indicate that the phase here doesn't really get all the way to 90 degrees. And then there's the resonance and secondary weird resonance up here near 10 megahertz. The important parameters for us are going to be what's the frequency of the mechanical resonance, what's the maximum phase we get to, going back to the magnitude plot, how big is the magnitude here, about what is the resistance here at the bottom part. We're going to want to have the slope and height of this line, and we're going to want to know either where this resonance is or what this curve here is doing in order to get the parameters for matching that peak. So let's get out a piece of paper here and draw out the schematic for what we're going to be doing. There's going to be a DC resistance, let's call that R1. There's going to be a mechanical resonance, and that's going to be a resistor, an inductor, and a capacitor. And let's give those names like RP, LP, CP. Okay, and then we're going to have this nonlinear inductor, which we'll do as M j omega times 1 second to the alpha. And for that final high frequency one, we'll put a capacitor in parallel with this. And let's just call that something like C2. Okay, so what we're going to need to do is we're going to have to construct this model. We're going to have to get initial estimates for each of these parameters, and then do fitting to fit the magnitude data, fit the model to the magnitude data. Okay, so let's take a look at the scripts we're going to do that. And there's two scripts. One of them is just kind of a framework script. It's going to load the fitting script itself, the one that has the model and all the parameter fitting that's going on. And then it's got some formatting stuff. We're going to plot the data with lines. We're going to plot it over the entire X range and Y range. Set the label for the Y range because didn't do that in the definitions file that the fit file calls, and set a format. So this is just making the plot look readable. Then I've got some parameters here, some labels. The unset label erases any previous labels that were around. And then setting the labels, one is for the mechanical resonance, just to remind me what the values were that I saw in the data file for that. It was around 157 hertz, and the peak resistance there was about 23.6 ohms. The 22.4 kilohertz, that's where the secondary resonance is that we're not going to be modeling. Then the 53 degrees is where that peak of the phase occurred, and that occurred actually at about 1 megahertz. So these are just kind of reminders to myself of those values. And then what I'm going to plot is the absolute value of the model, so we're plotting the magnitude of the impedance. Then we're going to plot the data from 100 hertz to 250 hertz, just from 250 hertz to the 100 hertz to 250 hertz, plotting frequency on the x-axis and the magnitude of the impedance, which was column 3 of the data, on the y-axis. And the last one here is plotting the rest of the data from 50 hertz to 10 megahertz, but I'm using this sort of weird conditional expression here to say if it's less than 100 hertz or greater than 250 hertz, so if the first column is outside that range, we'll take the data from column 3. Otherwise, we'll have this capital N, little a, capital N, which stands for not a number, and that will blank out that part of the plot. So we'll see in blue the resonant peak from that data, and we'll see in black the rest of the data. And these two curves, because they're separate data collections, don't quite line up. There's always a little bit of non-repeatability in doing different sets of measurements, but they come pretty close, and the blue data from the finer fitting of the resonant peak is much more precisely measured. We have a lot more data points in there than the more coarsely spaced data points for the whole curve. Okay, so now let's take a look at the oval fit file here that actually does the setting up the model and fitting it. So what we have at the top, we load definitions.gnu plot, which is the definitions of all the standard functions that we use throughout all of our mode plots. Then we want to get some initial values based on values from plotted data. So rather than directly getting my estimates, first thing I'm going to do is report what are the points I'm using, what are the data points I'm using from the data to set those initial values. So I have the frequency of the mechanical resonance here, 157.3 hertz. I looked at it a little more carefully to see exactly where that peak occurred. I did that by looking at the phase plot and looking at where the phase went through 0. And then how high was the resistance at that point? It was about 23.6 ohms. And then I define omega m to be 2 pi times f of m. So we have, for ease of writing later on, the angular frequency as well as just the regular frequency. I looked at what the maximum phase ever was in the inductor-like region. and that was just 53 degrees roughly. I have the frequency at which that maximum occurred, which was about 1 megahertz, and I looked at what the impedance was, the magnitude of the impedance was at that 1 megahertz or close to it, and it was about 183 ohms. These numbers don't have to be super precise because I'm just using them to get initial values, but I basically reported them to the accuracy that I had in the data file, or the close enough. I rounded a little bit to make it easier to type here. Then I looked at where that peak occurred, that high frequency peak, and it was about 3.28 megahertz. I also looked at one point at a higher frequency, about 5 megahertz, and looked at what the impedance was at that point as a way of trying to estimate the final capacitor. Okay, so those are all measurements just from the data, not trying to get them into the form of parameters for the model yet. Just these are data points that I'm going to try and use later on. The model itself consists of the resistor R1 in series with three things in parallel: RP, the inductor LP, the capacitor CP. And then in series with both of those, we have the parallel combination of the nonlinear inductor-like device and a capacitor. So M and alpha for the inductor-like device and C2 for the capacitor. And now I'm going to start getting initial estimates. For the R1 initial DC resistance, I just looked at where the left end of that curve was roughly and said it's somewhere around 7 ohms. Then there's the mechanical resonance here. And for that one, I'm going to use the frequency here because the frequency of the resonator, the angular frequency, omega m, if you square that, that's 1 over L times C. So I'm going to just estimate L to be 1 over omega m and C to be that 1 over omega m squared divided by LP. The reason I did it, I could have just said 1 over omega m for both and it would have worked. Same values as I've got here. The reason I wrote it this way is that now if I wanted to say, hey, I want to estimate L to be bigger, or I want to estimate L to be smaller, I only have to change one number here. And that would change both L and C while keeping their resonant frequency to be really at this FM, the frequency of the mechanical resonance. So this is an easy way to play around with those initial values. Turns out I didn't need to play around much with the initial values. Anything where L and C are close to each other within a factor of 10 or so of each other would have converged just fine. And then RP, that parallel resistor with the so the resistor that goes together with the inductor and capacitor here, I just said how high is that peak, Rm, that I had up at the top here, subtract off R1 because that's those are what you would see at that peak. And again, these numbers are not super accurate because it's not taking into account things like that extra inductor-like device down at the bottom. But they give a good starting point from which the fitting can then get all the correct values of the parameters. Finally, for alpha, I just estimated the alpha value as the maximum phase divided by 90 degrees. So if it had been a pure inductor and the maximum phase would have been 90 degrees, I would have had alpha as 1. If it had been a pure capacitor and the phase would have been minus 90 degrees, I would have had a minus 1. Here, because I had, 53 degrees, I'm going to have 53 over 90 as my initial estimate of alpha. And again, it's not precisely right, but it's going to get me very close to being in the right ballpark so that I can get convergence on the optimization. And then I just said, well, let's take a look at what the impedance was at that 1 megahertz and say, all right, let's make Z phase divided by, and this is now the omega to the alpha. And this would be the value of M that would make that nonlinear impedance, the inductor-like device, have about the right impedance. And again, I could have subtracted off a tiny bit here. I could have taken z phase minus r1, for instance, and divided that by this omega phase to the alpha. But I just need to be in roughly the right ballpark. I don't have to be very precise on these initial estimates. I print out these initial values. I was doing that because at one point I had a typo in the file. I had left out the period on the 90 and the period on the 53. So I'd done 53 over 90. But because GNU-plot uses the C convention that if the two numbers are integers, it does integer arithmetic, 53 over 90 was coming out 0. And for some reason, nothing was working, nothing was converging. And so I print it out and go, wait a minute, why is alpha 0? And it was because I'd forgotten to put in the decimal points to make them floating point. Just a little warning that's something to watch for. And it's always a good idea to print out values even when you think you know what they're supposed to be, because sometimes the computer and you don't always agree on what things are supposed to be. Okay, so the next thing is I've got two different ways of estimating that capacitor C2. That's the only parameter I've got left to need an initial value for. And this first one is a pretty complicated one, where I looked at what the resonant frequency of the inductor-like device and a capacitor in parallel would be, looking for a place where if you take the square of the magnitude of the impedance, you take the impedance times the complex conjugate of the impedance, take its derivative with respect to omega, and look at where the real part of that goes to 0. You get a lot of algebra and calculus, and eventually you come down to a simplified formula. That's this one. That's a kind of complicated thing, and it isn't really necessary here. Another way to do it is just, I have this extra f cap and z cap, which is just another point up on the downward slope where it was behaving like a capacitor above that high peak. And I just said, all right, pretend like that's on the line for the capacitor, and you just say 1 over 2 pi f cap z cap. And that's just, if this is a capacitor, what's with this impedance, what's the at that frequency, what's the capacitance that would give you that? And that's the one I actually used here from doing it. But I did print out both of them. And now that I've got initial values for all the different parameters, there are, let's see, 6 parameters in this model. I will just do a fit. And like I said, I'm not going to try and fit the stuff back where we have the dip at the very high frequency, so I'm just going to fit up to 4 megahertz. And try to fit all the parameters using the data set here that's got all the data in it. And then because I wanted to do the fit, treating all parts of the curve as equally important on the Bode plot, that means that I don't want a 1 ohm error at the low end to mean the same thing as a 1 ohm error at the high end. 1 ohm out of 7 ohms is a huge difference. 1 ohm out of 200 ohms or 300 ohms is not a big difference. So I want to do everything on a log scale. So I fit the log of the model, or actually the log of the absolute value of the model, because we're just fitting the absolute value of the impedance here. Fit the log of the absolute value of the model to the log of the data, and fit it with all the parameters, all 6 of them. Then I do the fit again on just the resonant peak. And here, because I was most interested in the top of the peak, getting the shape at the top of the peak just right, not that it really matters for anything we're going to use the model for, but I wanted to get a good fit. Here I use just the absolute value of the model, so that the higher you up are on the thing, the more important the errors are on the log plot, because we're treating it as if it was not taking the logarithm. And here I just fit the DC resistance and then the 3 parameters that correspond to the mechanical resonance. And the reason for throwing in the DC resistance is I want the whole thing to slide up and down, and R1 basically slides the whole plot up and down, whereas R1 plus RP gets the tip of the peak in the right place, and the LP and CP get the shape of the peak right. Okay, so this is a very simple fit. I'm not doing a lot of sort of fitting little bits and pieces of it at once. The example I gave in the book fits little bits and pieces, so I do simpler models, fit the simpler model first. Here I'm just fitting the whole model all at once. And to fit the whole model all at once, the crucial thing is to have good initial guesses. And I think that the method I used here for getting initial guesses for all those parameters worked fairly well. So let's let me go and look at GNU plot terminal and just load that plot. It does a bunch of fitting. And now let's take a look at the curve we get. And maybe I can make this a little bigger. We've got this version of GNU plot doesn't like the ohm symbol, so it's messing those up. I've got a very nice fit here. The blue curve and the purple curve are right on top of each other. So that's the resonant peak. That extra fitting I did there made that fit really well. The region in the middle here, it's a decent fit, not always perfect, but given that I'm using 6 parameters to fit, and 3 of them are used for mechanical resonance and 1 of them is used to fit that resonance at the top, I basically only have got 3 parameters left to fit everything. 3 parameters left. So it's a 7-parameter model. The M and the alpha is 2 parameters for that component. 6 components, 7 parameters. The peak up at the top is not super well fit, but I wasn't really trying to fit that dip again at the very high frequency. So overall, I'm pleased with this fit, and it was an extremely simple one to get to work. Now, some things we want to check after doing this is, we've got this model. Does the model match the phases as well as the magnitude? And we can look at that with another plot. So let's hide those things, and we can do a phase plot by looking at doing the same fitting with overfit GNU plot, but now our Y range is just going to be from -90 to 90 to get the phase in degrees, and what we're going to plot is the phase of the model. Now that usually comes out in radians, so I have to multiply by 180 over pi, and it's column 2 now rather than column 3 of the data that we're going to plot to match that. So I will go back to the GNU plot terminal, and instead of loading oval mag Z, I'll load oval phase, and it did the same fitting as it did before because it's running the same file. And here's what we've got. Again, it's not a perfect fit, but it's pretty good given the small number of parameters we're using to fit what's really quite a complicated curve. And again, once we get up past about the 4 or 5 megahertz here, the fit just goes terrible because we put no parameters in there to try to match that high frequency change in behavior. Actually, it might be worthwhile to take a look at a model that does include some extra parameters to try and handle that high frequency glitch. So let's go back to looking at not this model, but the curve again here, and we've pretty much fit everything up to this point. Now to fit this point here, we're going to need to have some sort of resonance. And because it's a resonance going down rather than a resonance poking up, that means we're going to need something like an inductor and a capacitor in series. And at this very high frequency, we're mainly being dominated by that capacitor C2. So we can just take the model that we have here and add 1 or 2 more components. Instead of C2 here, we can put C2 in series with L2. That would give us a resonance, though, that went all the way down to 0. and we don't really want to do that. I mean, that resonance that we had there only went down to about 90 or 100 ohms. So let's put a resistor in here as well. So we've replaced the capacitor now with a resonant tank circuit here that's going to have, we can tune this one to have its resonance be right where this thing has its minimum. We can set R2 so that the minimum is at the depth that we're seeing here, and then the C2 and L2, we can trade off how much C2 there is and how much L2 there is to change the shape of the curve a little bit there. So it doesn't require a lot more complexity to our model to try and model that extra high frequency stuff. So let's see if we can get up a model of that. I did type one up. And this one is a little more complicated because the model is more complicated. We start out again with the measured data, the points that were there, but we've added now, in addition to the F cap and Z cap that we had for the downward slope where it was behaving like a capacitor, I've added the frequency. Where does that minimum frequency occur? And it's at about 7.9 megahertz. And what's the impedance, the magnitude of the impedance at that? And it was about 89.5 ohms. And again, this was from looking at the data file to see where that high frequency minimum occurred. And again, it doesn't have to be very exact. I mean, the data file will fit this thing by adjusting the parameters. We just have to have it so that the initial values are close enough that the fitting can converge. Our model now has replaced the nonlinear inductor in parallel with ZC with the nonlinear inductor in parallel with the C2 capacitor, the L2 inductor, and the R2 resistor all added together. Okay, and we've got the same initial estimates that we had before. Let me slide this up a little bit so you can see more of it. Same alpha and M estimates before, and we'll even use the same C2 estimate that we used before. So we're only thing we're adding is new estimates for L2 and R2. And for L2, I just took that resonant frequency, the 2 pi f min, squared that, take 1 over that, and divide it by C2. So that's just saying make the LC resonance, which is omega squared is 1 over LC. Set the L to get the resonance just where we want it. And then for R2, I just made that the Z min there minus R1. Again, we've got the DC resistance always being added. And I'll do the fit now, not stopping at about 5 megahertz, but going all the way to the end, fitting all the parameters. So I've added 2 more parameters. Then I have fit the absolute value of the model over the just the resonant peak to tweak that. I tried doing a little bit of tweaking here, but I've commented out that tweaking. We can pretty much ignore this stuff here at the bottom. So let's just slide that down so you don't even see it, because it's just comments, it doesn't appear. I tried adjusting C2 to see if I could get a better fit, but I couldn't manage to get any fit that was any better than the automatic one, so the automatic one will do. All right, now let's bring up the GNU plot terminal. And I need to do one other thing. I have to look at the magnitude thing here. Instead of saying oval fit, I've got to say oval fit 2 because I'm fitting a different model from a different file. So let's save that and load that. And it's done the fitting, and let's bring up GNU plot again. And now, not only do we fit this mechanical resonance, but the electrical resonance is not too far off either. And this dip at the top here fits right on. So we've got now a really good model, and it's using 9 parameters. We added 2 more to the 7 parameters we had before. And with 9 parameters, we fit this peak, this gradually increasing curve here. The almost fit the peak here. It's the data is a little bit more peaky in the resonance than what we modeled it, and fit this dip quite well also. So that looks like a pretty good fit. We can do checking the phase again also. So let's hide that plot and bring up the phase. We have to edit that to do oval fit 2 also. And now we can go back to GNU plot and load oval phase. And it does the same fit as it just did. And if we look at GNU plot, we've got decent fit here. Pretty good fit given how few parameters we've got. The phase is not matching quite as well at this capacitive region. What we're getting here isn't quite as capacitive as the data is. The data gets down to minus 60 degrees, and we're only getting down to minus 40 degrees. And we're not getting, I mean, the whole curve here is a little bit up on the phase. So while we had that thing that looked like a really good fit at the high frequency stuff for the magnitude, it's not such a great looking fit for the phase. But it's still pretty good. It's capturing the overall characteristics of this thing, and it's certainly a usable model for just about anything we might want to do with it. So, bottom line on this one, if you can get good initial values for your model, you can fit the whole model all at once, which is different from what I did in the book, where I fit a little bit at a time just on the part of the model that some of the data was doing, to try and bring people's attention to which part of the model corresponded to which parts of the data. But if you get the initial values right, you don't have to do that. You don't have to break it down in bunches of little fits. You can just fit the whole thing at once. And that's pretty much it for fitting loudspeakers. You'll be wanting to do this with your own data. Notice that I didn't use any of the phase data in doing any of the fitting here. The phase fit here is coming entirely from the characteristics of the model. And all the fitting was done with just the magnitude data. So it's actually kind of surprising that the phase fits even as well as it does. And that's it for this video.